And I'm going to present now a kind of follow-up of the conclusion of my first presentation. For those that were here, I was talking about the review of the technology to produce stereoscopic panoramas for human viewing, and with the particular twist of including dynamic scenes in the problem. In that case, I conclude that, well, a multi-camera approach using a reduced number of stereoscopic samples partially overlapped could be mosaic into a full omnistereoscopic image. And using the mosaicing approach actually is an easy approach to do a frame-by-frame rendering and then enable omnistereoscopic videos. So there are remaining two problems in that case, and that was a follow-up that we start working after doing this literature review of the technologies. One is how to mosaic these partially overlapped stereoscopic images, maintaining a consistent depth in between mosaics. So basically, you don't want to see artifact. If you see artifact, that is a sign that there is something going on there. And as you see in the example I showed of that stereoscopic panorama, there were no noticeable artifacts, at least no very noticeable artifacts. There are artifacts still that they are difficult to erase. But that was done with the prototype. So I decided to go into modeling this, how to model how much depth, or how to maintain the depth illusion in between mosaics. And also another problem that is a regular problem in panoramic vision, that is, or at least in stereoscopic panoramas, how to deal with the vertical disparities, or at least how to explain where these vertical disparities came from and where you are expected to find those vertical disparities. So we propose a model, a very simple model to start with, and usually those models are the models that work when they are simple and they present something meaningful or give some meaningful results. And that model that I'm going to explain now is based on basically two cameras and a stereoscopic rig. And with that, you can explain the majority of the technologies I explained in my first presentation based on horizontal stereo. And we have some experimental results based on simulations to test this model and to extract some conclusions. And that basically is the roadmap of this presentation. Basically, the model consists in this, in two pinhole cameras separated by a baseline. In the center, we have the reference viewpoint of the panorama. And these two cameras could represent a rotated pair of cameras around that center, or with certain displacement, it could represent the real case of a multi-camera system in which you cannot align or you cannot position these cameras all together, given the dimension of the cameras, in the nodal points. And well, we had the reference for each one of the cameras, and a point in the space and in the scene could be projected into these two image planes. And using projected geometry and simple equations, basically we can infer a result. Basically, the horizontal disparity, we can calculate the vertical disparity for different configurations. And the different configurations are these. This simple model could be expressed in 4 forms. And we found that with those 4 forms, even though it's difficult to believe, but it could represent most of the technologies we were, well, I was talking in the first presentation, but not those technologies based on vertical parallax. But I don't care about those technologies because basically we were interested in the horizontal parallax problem. So the first case is 2 cameras that could be rotated. There could be a multi-camera approach. Actually, this is difficult to implement in the multi-camera configuration. The second one is basically shifting this and start rotating the cameras around the center. And one of the papers from 1998, the things that was basically could be modeled with this configuration. The other configuration is displacing this a radial distance RC from the center. And that basically represents that in a multi-camera approach based on this configuration, on this stereoscopic rig, when you put multiple stereoscopic rig around that virtual rotation center, the case in which the nodal point of these cameras cannot be in the center all the time. In this case, for example, you cannot represent this a multi-camera approach because all the cameras cannot be around coexisting in a space, co-located in a space with the same nodal point. And the last case is basically this one rotated when shifted BW2, B divided 2 to the other direction. So basically you have this stereoscopic rig, one is centered in one of the cameras and the other is centered in the midpoint in between the nodal points of two cameras. These 4 configurations, for example, let's take this last configuration, configuration 4 that I was showing before. Well, this represents a single rotating stereoscopic rig at that distance with respect to the center, a multiple cameras approach, which each one of the cameras have certain spatial location with respect to the other stereoscopic rig, which is this multi-camera approach, or this multi-camera approach where multiple n number of cameras rotated around the center or fixed around the center, all represented with the same model. Let's give an example. So let's say that we have this model, and we have 2 sequential acquisitions separated by an azimuth angle of theta sub e. So we have one pair of the same, one stereoscopic pair and the other stereoscopic pair. Now, let's say that in that configuration we decided to take 6 samples, 6 stereoscopic samples. And this starting by 0 to 5, we have 6 stereoscopic samples of the same, partially overlapped, constitute these 2 sequence of images, and this is the data set we acquired. Could be sequential, could be simultaneously. Now, what areas when we start mosaicing this, we can differentiate? We have an overlapping region here when the point in the scene is visible by the 2 stereoscopic rigs, or by 2 samples of the scene. And these areas that are visible by only one stereoscopic rig at a time. When we mosaic, we can define a fixed position where to mosaic. That depends on the number of stereoscopic samples. In this case, it's this position in between the scene. This is the image. This is the reference center of the image, and this is a position that is symmetrically located with respect to the center. Now, is that the optimal? No, it's not the optimal. It's a position reference that you can use. I said you have 6 stereoscopic samples, and you have this width of the image, and then you can basically by eye say, well, this is the point when I had to stitch all the images in order to create a 360-degree view of the image at least in azimuth. But it's not the optimal point. Or we can see that those points that we saw before, well, these P2 and P3 are the points that are visible only by, in this case of P2, by this stereoscopic rig, and this P3 by this. And P4 is the one that is in the overlapping region of the 2 images, which I call the omnistereoscopic field of view of the whole arrangement. Now, coming back to this model, any point of the scene could be represented in the reference frames of each one of the cameras by this equation. With R is the rotation. In this case, the 2 cameras are restricted to be in the XZ plane, and the theta sub I represent the azimuth sample angles in between the 2. Y is always parallel to the Y, to the global reference frame. So basically, the 2 cameras are restricted to one single plane, and they have the parallel axis, and basically they are rotating in this direction. So you can be represented all the different positions by this single equation. And by this translation, they represent the translation in between left and right. From these relative coordinates of the scene in each one of the cameras, you can, using projective equations, find the coordinates in each one of the image, the X and Y coordinate for the left and right for each one of the theta sub I. Following up that logic, you can talk about the horizontal disparity error, which is what is the difference in a horizontal disparity that is going to be in the overlapping region of the images, or 2 images or 2 stereoscopic pairs that we need to mosaic. When that difference is larger than the threshold of human resolution of horizontal disparity, then it's going to be noticeable. If it's below what we can perceive, therefore it's not going to be visible, and we can stitch it safely. So we can infer what is the horizontal disparity expression from those previous equations for theta sub I, for any theta sub I, and then a theta sub I plus 1. So for 2 consecutive samples in any the symmetry of the problem, we just need to study 2 consecutive samples. There are certain simplifications that could be done here. For example, the set or the depth with respect to one stereoscopic pair, or the left or the right, is going to be the same. So we can reduce this to this singular distance with respect to one single camera, and it's going to be different than the one that is seen by the other camera. And then talking about the error, the absolute difference between these 2 magnitudes. When manipulating the equations, you can reach something very simple, which is the horizontal disparity error is dependent on the difference of the reciprocal of the depth as seen by each one of the stereoscopic pair. Now translate it to each one of the 4 variations of the same model, and then you can describe all you want, at least in terms of horizontal disparity. Now, what is the threshold of horizontal disparity in humans? And that is a nice topic of research, because basically in some literatures, I found that, for example, well, this equation came out by comparing the same basic parallel optical axis stereoscopic pair model using pinhole cameras with the resolution of the human eye based on psychological studies, based on several tests in certain group of humans with certain selection of images. Whether those images have certain texture or not, and well, that number changed. But the evaluation, when you put the 2 equations together, you can reach a horizontal threshold. This is the error, the threshold in the horizontal disparity error that human perceive based on this pinhole stereoscopic pair and the human model, which is baseline, the baseline between the human eyes, and this is the distance between human eyes. So basically, if the baseline of this virtual stereoscopic rig is the same, then the distance between the interocular distance between humans, well, you can simplify this. This parameter is the angular resolution perceived by human, and that threshold is about 20 arc of second, which is quite slow, quite low. And this number here of threshold gives something that is 25 times smaller than the width of a pixel. So basically, it's not useful. It's not usable in this form. So this is going to be lower than the width of a pixel for a regular camera. You cannot use it. So what we did was move to use the width of a pixel as a threshold, which is a practical approach, given that that width of the pixel is basically what we need when we mosaic stereoscopic images. If the error is larger than the width of the pixel, it's going to be noticeable. If it's low, it's not going to be noticeable. And it happened also that it maintained the continuity in the horizontal disparity. So if you consider something larger, 25 times larger, that 20 arc of second is close to 1 arc of a minute of resolution. So we said, probably that is the correct one, the correct answer, given the technology we had today. And basically, it looked good, so it must be correct. So we start simulating, based on our model, using that threshold of 1 pixel, for this particular camera, using real numbers, the sensor width of this Canon 400D, and an angular field of view based on a fisheye commercial lens that we could use in our experiments, and in a baseline of more or less half the interocular distance in the human adult population, 35 millimeters, and a radial distance for this particular configuration 3 and 4 equal to the baseline, so 35 millimeters. So we tried to compare the different cases, and we came out with this plot. The R minimum is the minimum distance between the scene and the camera for to have a continuous horizontal disparity. So basically, what we are plotting here is that the difference between the point we choose by eye, that XB, no, in the image, moving 5% toward the center of the image or minus 5% toward the edge of the image. And that correction gives us these plots that, for example, if we are using that point, choosing deterministically, we found that, for example, the configuration 3, and the configuration 3, for example, the scene had to be 2 meters from the scene when you use 6 samples. When you use 8 samples, basically that overlapping region moves closer to the center of stereoscopic pairs, and that changes a little bit closer to the camera. So that is important? No, it's not important, because basically, for practical reasons, if I build a camera and I want to determine one model is better than the other, or one configuration of multi-cameras is better than the other based on this, I will say, well, I really don't care if the scene is 2 meters of the camera or 1 meter from the camera, unless I'm doing micro omnistereoscopic images where things are very close to the camera and the things are small. But in normal cases, if I put my camera here and I want to create an omnistereoscopic image of you guys over there and me here, and I am at 3 meters, well, I'm not going to have any problem if I choose that threshold to mosaic the images. But it had to have some uses. Well, the use is basically the other thing that we were interested in using this result to say we can define an optimal cut for the mosaics that is based in an energy function that consider this horizontal disparity resolution in humans. So when you introduce that into the algorithm of optimal cut, the same scene could be cut in a different way when you mosaic for elements that are closer to the camera and elements that are far away from the camera. You can find the point in between 2 mosaics where you can basically blend them and then make invisible any artifact that will happen otherwise if I use a fixed stitching point. And basically you can port this for each one of the models for all the configuration you can imagine. And I thought, well, that is an interesting result. The other is the vertical disparities. Vertical disparities in panoramas always appear. But based on this model, the vertical disparities, based on a stereoscopic vertical disparity, in the stereoscopic area of each one of the cameras should be 0. Because based on this equation, the projection on the image plane, this value and this value of the distance of the scene is equal to this. For each one of the stereoscopic pair, we say that the set is equal to each other. So this value simplifies, and basically, if they are aligned, happen that in reality this never happened because the optical axes are not really parallel and they are misaligned, so you have to do some correction, some stereoscopic registration. But if you do that, basically you wouldn't have any problem in these areas. But you will have problems in the overlapping areas. And that problem happened not in between left and right, but in between in the left sequence of images and in the right sequence of images. And that happened when you do this comparison. You see this expression, that gives this number is a multiplicative factor over this y. Y is the elevation with respect to the center. When we are talking about the equatorial area here, it should be 0. So it's going to be aligned. But the more you look up or you look down, you will have a multiplicative factor that affects that, and the larger is going to be the disparity, and the more you need to warp the images in order to make it align. But we are talking again with respect left to left, right to right. And to see this graphically, you see when the scene is far away from the camera, that effect doesn't matter because basically that disparity is going to be not noticeable. But when you're taking a panorama here and imagine what happened in the roof or in the floor that are closer to the camera, meaning closer distance from the camera, this is R is the distance to the camera, the multiplicative factor is going to be larger. And that would explain what it's always look misaligned and always had to do some kind of warping in that direction. I'm talking always when I don't have extra information about the depth in order to match pixel to pixels. All right. And here you see what happened at different distances. So basically, all this analysis was to put together a model that could represent all the different omnistereoscopic technologies with horizontal parallax that is flexible and simple enough to represent this. We came out with a result that could be used for the device at optimal cut, and we explained some issues that happen with vertical disparities. And well, that is my presentation, and I hope you enjoyed it. Thank you.